Hi everyone and welcome back to the channel. In today's video, we'll be going through a review of statics. Specifically, if you're taking the mechanical, civil, or other disciplines exam, this review will be useful to you. You can see the NCES specification here, labeled A through F for the different subsections, and I have numbers on the right-hand side. That's the problems that's going to be associated with that section. So there's 8 problems in total, and there's additionally timestamps in the description so that you can jump to whichever problem or topic that you're looking to review. The different topics that we're going to be covering here inside of this review is understanding the idea of vector addition, slope triangles, the difference between pound force and pound mass in the English system, because definitely there's English system problems on the FE exam, Newton's second and third law, the different support types that you'll encounter, moments in 2D and 3D, trusses and frames, centroids and moment of inertia, and static friction. You can see on the right side of the screen here, there's some diagrams from a subset of problems that we're going to be using as practice to review from my software FE Interactive. The general format here is, you see a diagram and a question, as well as the choices associated with that question. And on the FE exam, most of the questions are going to be multiple choice. So we have those multiple choice questions here. And on the right side, I kind of highlighted the relevant section here. So this question in particular is related to subsection D here, frames and trusses. Now you can try all of these problems using the first link in the description below. The FE exam is really all about practice here. So once you click on that first link in the description below and you want to access the entire review here, you're going to click filter, statics, and collapse. And that'll show you all of the questions here that we're going to be doing in this review. You can use the flag button in the upper left. Without further ado, let's go ahead and get right into the problems. Okay, so moving on to this first problem here. The first one, we're really going to be covering the idea of resultant force systems. And you can see here that in this problem, if we quickly read it over, it says a particle P is experiencing a net force of 120 newtons. So that's this red kind of 120 resultant here. We want to decompose that resultant along the directions A and B. And if you look at that direction A and B, they're non-orthogonal directions. It says the resultant magnitudes FA and FB are most nearly. Okay, so this problem is really all about understanding vector addition and recalling the parallelogram rule of vector addition, which says that if you have two vectors that are being added together, like a vector along the direction of A and a vector along the direction of B, then what you could do is do their tail to tip sum, right? We take the tail of the second vector and add it on to the first vector. Really, how I like to think about it is you kind of start at the center of the origin P and you travel along the A direction until you hit the end of the first vector. Then you travel along the second vector. And they call it the parallelogram rule because you can kind of go along the other direction as well, right? You can travel up the B direction and then down the A direction here. And that would form a parallelogram. Half of a parallelogram is a triangle, and that's what we're going to be working with for this problem to find these unknown magnitudes, FA and FB. Now, how we're going to find FA and FB is we have to understand some of the angles inside of this triangle. And once we understand the angles, then we're going to apply things like the law of sines or cosines to get the answer. And we're going to more lean towards the law of sines since that's a lot faster computation here. So the first thing here is this is a supplementary angle, the 80 and 40, that makes 120 degrees. And we know that this vertical line has to add up to 180. That must make this 60 degrees here. All right, so now that we know that's 60 degrees, what about this angle down here? If we wanted to find that angle there, that's going to be the same as this angle here, the angle between the vertical and the direction of B. Now, you could see again, we have another supplementary angle here, the 80, the 60, that sums to 140. And we know that the entire thing must sum to 180, so that this must be 40 here. And if that's 40, this also must be 40. The sum of all the angles in a triangle must add up to 180. So I'm seeing the 60 and the 40, that makes 100. This 80 would make up the rest of that triangle. We understand all of the angles inside of this triangle, so we're going to go ahead and apply the law of sines here. What we have is one of the side lengths, that's 120. If we go ahead and divide that by the angle opposite that side, that's the sine of 40 degrees. That must be equal to the same ratio for the other sides. So that'll be FA over the sine of 80 degrees. And that must be equal to FB as well, divided by the sine of 60 degrees. We can go ahead and solve for FA and FB here. And what we get is that FA is just the sine of 80 divided by the sine of 40 multiplied by 120. And FB is the same thing, but we replace that numerator with the sine of 60 instead. Okay, multiplied by 120. Let's go ahead and plug this into the calculator and see what we're going to get. 120 multiplied by the sine of 80 divided by the sine of 40. Okay, so I'm getting around 184 newtons here when I round it. And let's do that same thing. We'll replace that 80 with a 60. We get around 162 here. So if we look at the choices, FA is 184, FB is 162. That's this choice D here. So that would be the answer here. Another note here is that you can see that all the FAs and FBs are unique. So you really only need to find one of them. But for completeness, we went ahead and found both of them. This problem was super important to reviewing the idea of the parallelogram rule of vector addition. And sometimes we don't break down these forces into a perpendicular system or Cartesian system, and this was a good reminder of that. Let's read through this problem. It says the system of cables above is used to support masses D and E, which are 100 pounds and 200 pounds. Let's go ahead and label that. So this one is 100 pounds, 200 pounds. The magnitude of the tensile force in cable BC. So if I kind of label that on the diagram here, it's as if we made a cut here. We're kind of looking for that tensile force pointing out at that cable. Okay, we have a few different things to address in this problem here. The first thing that I'd like to address is this slope triangle here, right? And how we kind of use that. A lot of people, they go ahead and, find the angle there and make it more similar to this side, but it's really not necessary and it's kind of a waste of time. So if you have a triangle here and you denote one side of it as theta, and you go ahead and write down the sides of that triangle, 3, 4, and this is a Pythagorean triple here, 3, 4, 5 right triangle. You can write down by inspection that the cosine of theta is adjacent over hypotenuse, that's 3/5, and the sine of theta is opposite over hypotenuse, that's 4/5. So that's how you use that. So you can kind of directly use those cosines and sines of theta, just substitute those in to your equation here. The next thing is that, in the upper problem, we were breaking it down into kind of an arbitrary triangle. But in this problem, what we're going to do is whenever we can, we want to break it down into a Cartesian system, the components of those forces, and apply Newton's law in the x and y direction. And that's because orthogonal systems is like breaking everything up into right triangles. Right? Right triangles are super simple to work with. No law of sines or cosines, just regular cosines and sines. All right, so the first thing in problems like these is we're going to want to draw a free body diagram and one that's going to expose the force of interest here. So if we go ahead and make a cut at that joint C, what we're going to do is we know that cables can only support tension. So for instance, this lower cable, let's say we were drawing this kind of section of cable right here. We have a lower cable here, and we know that cable is being stretched. By Newton's third law, we know the force at that joint is going to be, kind of like this, pointing downwards here, and this would be the joint C. Right, so those equal and opposite forces would, when you overlay them back on the back at point C, you would see them become self-canceling. So that's why forces pointing away from the joint are always in tension, right? We draw a nice clean free body diagram here. All right, so in order to find that force BC, we're going to be summing forces in the x and y direction, and that's going to give us two equations, two unknowns that we're going to use to solve for that FBC. But it's not important in the English system whether these are masses or weights because their values turn out to be exactly the same. So your assumption could be their masses, their weights, and you would be correct. And the reason for that is because 1 pound force is the amount of force necessary to accelerate 1 pound mass at 32.2 feet per second squared, right? This is just the normal conversion that we use to go from pound mass to pound force. And we know that weight is equal to mass times gravity. So the upper portion, this is just representing a conversion factor between pound force and pound mass feet per second squared. It's kind of akin to having a Newton being equal to 1 kilogram meter per second squared. You could see the difference between the metric system and the English system is that they've included this gravity term inside of the definition. So it makes things super confusing. Let's say, for example, we plugged in the mass as 100-pound mass here. And in order to turn mass into weight, we multiply by gravity. That's 32.2 feet per second squared. So on this right-hand side for the weight, what I have is 100-pound mass times 32.2 feet per second squared. If I wanted to convert that into pound force, I know that a pound force by the conversion factor above is 32.2 pound mass foot per second squared. The pound mass foot per second squared cancels out. The 32.2's cancel out. So you see gravity cancels out. What we end up with is that 100-pound mass is equal to 100-pound force. So that's why we can go ahead and assume that's mass or that's mass or weight. It doesn't really make a difference here. I'm going to move all this stuff over so we can write down the two nice clean equations here. Let's start off with the sum of the forces in the x direction. Sum of the forces in the x direction here must be equal to 0. So if we sum the forces in the x direction, we're going to get a positive FBC here. FBC, it's like a cosine theta, which is a 3/5 here. FBC 3/5 component minus FAC, which is pointing to the left side, that's sine of 30 degrees. That must be equal to 0. And the sum of the forces in the y direction is, we're going to have a few more components here. Let's start off with the FBC. FBC, it's kind of a sine theta component, which is the 4/5 plus FAC, cosine of 30 degrees, minus 300. That must be equal to 0. Okay, if we substitute in for sine, the sine component is 1/2 sine of 30 degrees, and the cosine component of 30 degrees, that's √3/2. Okay, so our goal is to just solve for that FBC. If we multiply the upper equation by square root of 3, we'd be able to eliminate the FAC by summing the two equations. So what we'd end up with here is FBC. We multiply that upper equation by the square root of 3. So 3√3/5 plus 4/5. When we go ahead and add these two equations together, the second term, the negative FAC and the positive FAC, they're both a √3/2 term after we multiply that by √3. So that's good. And now that's equal to, I'm going to move 300 to the other side here, 300. So FBC is essentially equal to 300 times 5 is 1500 divided by 3√3 plus 4. So this should be the answer here. All right, so I get 163 here. 163 pounds approximately. That would be choice A. In this problem, we're looking for the magnitude and direction of the wall bending moment, and we're given a cantilevered beam here with a distributed load, triangular distributed load, as well as a concentrated moment and a point load. And we're given some of the distances, and we're just asked for the magnitude and direction of the wall bending moment here. So clockwise or counterclockwise, and uh, the magnitude of that couple. Okay, this is a good opportunity to review support types. We have a cantilever here. Another common support you might see on the FE exam is a pin support. Uh, Another one is a roller support here. And then, of course, we have the cantilever system. And we have some 3D supports as well. But, what's really important is to understand how you come up with the support reactions. When you restrict a motion, you have to introduce a reaction force, right? So you can picture a pin would restrain left and right motion as well as up and down motion. So it makes sense that we would introduce a reaction force or reaction forces in the x and y direction because we're restricting displacement in the x and y direction. The roller support allows motion left and right. It can kind of slide along these rollers here, right? So you would expect that we'd only restrict vertical motion here, right? If you're pressing this thing into the floor, you'd expect that there's no displacement vertically. It'll provide a reaction vertically. Now, when you restrict displacements, you introduce forces. When you restrict angles, you introduce moment reactions, right? So, of course, at that fixed end for a cantilever, for example, we'd have no displacement. So, of course, we'd have X and Y reaction forces. But additionally, there's no angular displacement at a fixed end or welded location. So you'd expect additionally there'd be a moment reaction. Okay, so that was a quick review of kind of typical 2D supports you see on the FE exam. Now, let's go ahead and discuss the distributed load and the couple, right? And the really important idea of statically equivalent systems. When you have a distributed load, what you're going to want to do is for the force to be the same and for the moment to be the same in your statically equivalent version of that system. Now, the magnitude of the force in a distributed load is just the area under that distributed load, kind of the load distribution. This triangle has a height of 3 and a base of 2. So that would be base times height divided by 2 would give us a force of 3. So we know that force is 3 kilonewtons, and it's going to be placed at the centroid of the distribution. This is a triangle here. So I always remember the 1/3, but some people get confused on whether it's a third of the way from the big side or the small side, right? And how I always remember it is at the centroid, you know that left and right of the centroid point, their moments must balance, and that's why this is considered the centroid, right? This area, this large area is producing a moment about the centroid. You could place its total force at that little area centroid. That'll be this large force placed at a close distance, and the small area is also producing a moment here, but its centroid is closer towards the left side, or it has more distance compared to the large area, right? So this small force placed at a large distance must balance this large force placed at a small distance. So that kind of idea of distances is um, how we know that we place it a third of the way from the big end, or that's how I kind of think about it. Okay, so we know it's a third of the way. Additionally, you could check the FE reference manual. There's information about centroids, but I would recommend that you just kind of, intuitively understand that this 3 kilonewtons where it's placed on the triangle, you have the idea of a third in your mind and you place it near the big side, right? Because the small force needs more distance. So you want to place it at a larger distance away from that. All right, so that's the idea of distributed loads and really goes back to the fundamental idea of statically equivalent systems. Additionally, if you look at a couple, right, what does a couple come from? A couple is like placing two equal but opposite forces at a certain distance away. equal but opposite. So both of these would be magnitude of force, magnitude F, placed at a distance d. The statically equivalent version of that is the sum of the forces in this system on the left-hand side has to be the same as the sum of the forces as the system on the right-hand side. So that upward and downward force sum to 0. So there's no force on the right-hand side, the statically equivalent version. And the sum of the moments must be exactly the same about any point. If we take a moment about this point right here on the left to eliminate this left side force, what we get is a magnitude, a moment with a magnitude equal to F times D, pointing in the counterclockwise direction, right? So that's where the idea of a couple comes from. It's just a statically equivalent version of this kind of equal but opposite force placed at a distance away. Okay, so let's now move into kind of solving the problem, right? Whenever you start off with a statics problem, most likely you're going to need a free body diagram here. So let's go ahead and draw a free body. What we have is a beam, and that beam will have reaction forces. There'll be a reaction force in the y direction, a reaction force in the x direction, and I'm seeing all of these forces are clockwise. And the moment, the concentrated moment, is clockwise as well, so I'd expect the wall bending moment to be counterclockwise here. This would be the moment at the left wall A. There's a force here placed at a distance of a third from the right end or 2/3 from the left end, and 2/3 of 2 would be 4/3. So this distance right here is 4/3, 4/3 of a meter. And then let's start off from the left end here. We have a clockwise moment here. And 2 meters from the left end, what we have is a 5 kilonewton point load. This is 2 more meters, and then this is a third. 2/3 of a meter. Okay, 4/3 and 2/3, that makes 6/3 or 2 meters. So that distance makes sense. There's an additional 2 meters here and 2 meters here. Okay, so the easiest way to find that moment at the left side reaction is we're going to sum the moments at point A. And when you sum a moment about a point, all the forces intersecting that point produce a zero valued moment because they have a zero valued moment arm. If you sum the moments about that left point here, we'll be writing the sum of the moments about point A, which is that left side wall, must be equal to 0. Let's pick counterclockwise as our positive direction. So we have that moment, MA, right? The MA isn't going to disappear because we took a moment on top of it. The couples just, they exist inside of the moment equation, regardless if you take a moment at the point that they exist. I'm seeing a clockwise 10 kilonewton meter, so let's write down minus 10 here. And then we have a clockwise moment produced by that 5 kilonewton term. So that's 5 kilonewtons multiplied by its moment arm, which is 4 meters. And lastly, we have another clockwise term here. It's clockwise, so it's negative. A clockwise term equal to 3 kilonewtons. So I'm going to put a minus 3 here, multiplied by 4/3. That all must be equal to 0. So the moment about point A is equal to 10 plus 20 plus 4, which is equal to 34 kilonewton meters here. And we know that the assumed direction of MA is going to be counterclockwise. So 34 counterclockwise should be the answer. All right, in this problem, we have a box with a constant density. It has a weight equal to 800 newtons, and it's suspended via 3 cables at the common suspension point E, which is 1.7 meters above the mass center. Its top surface is perfectly level. The tension in cable AE is most nearly. So if we remove the cables from each of these corners of the box, we'd kind of have a force here, just like that, and like that. So these forces are very three-dimensional, and it looks like we're gonna have like uh, 9 different equations, 9 unknowns, because each of these different forces, right? They have a force in the x, y, and z, right? They're a three-dimensional vector. They could have 3 components, and it looks like this problem is going to be super difficult. But whenever you have a problem like this and you're asked for just a single force, you're really going to be thinking about where's the place where I could take a clever moment that will allow this problem to turn into a very simple problem. All right, let's take some of the information that they gave us and place it onto this box here. The first thing is that we have this thing has a weight equal to 800 newtons, and that's going to be placed at the centroid. We're told that this box is nice and flat here. So we know that the centroid of this box is just going to be right in the center of this box. Everything is nice and flat here, and it's kind of going to be intersecting that point E at the top. This total distance is 1.7. So that means that this distance here, right? The distance from E to that 800 is 1.7 meters. Okay, we have some of these kind of three-dimensional forces, and what's important to realize is that we can take a clever moment and just find that force that we're looking for, that force in cable AE, which is back here. Remove this stuff. This is that force in cable AE. Okay, so remember that we can take moments about points or we can take moments about an axis, right? Usually, in a two-dimensional system, like in the problem that we did above, we took a moment technically about the z-axis, and we can align our coordinate system to have a clever axis that will eliminate these forces that we don't care about along that line BC. So if we choose our coordinate system to kind of be like this, where we have an x this way, let's just put the y pointing up and a z pointing parallel to that line AB. The best thing that we could do here is take a moment about the x-axis here. And if we kind of picture the components of that force AE, there'd be, let's just draw that in green here. There'd be an x, fx, let's just call it. There'd be an fz, and there would be an fy. And if you can kind of picture all of those forces here, remember that moments produce rotation about an axis, and that's how you know that it's going to be producing a moment, right? The force in the z direction for that, for the components of FAE that we're looking for, that'll intersect the x-axis. It can't produce rotation around the x-axis. The force in the x direction, that's parallel to the x-axis. It can't produce rotation around the x-axis. Only that force y will be producing a moment or rotation around the z-axis. And you can see that those other two forces are intersecting the x-axis, so they won't produce any moment. But that 800 Newton, it's going to produce a moment, right? Let's go ahead and let's write down the sum of the moments about the x-axis here. Sum of the moments about the x-axis must be equal to 0. You can see that that 800 and that Fy are the only things that are going to be producing moments here. We can do 800 newtons multiplied by half of this distance right here, half of 0.6, which would be equal to 0.3. That moment produced by the 800 is going to be kind of rotating the z-axis in this kind of direction, right? If you can picture it, it's going to rotate around that axis in the negative x direction, right? Using the right hand rule, you can curl your fingers in that direction. Your thumb will be pointing in the negative x direction. The force y is doing the opposite. If you can picture, it's curling in a direction where your thumb would be pointing in the positive x direction in that orientation. So it's producing an opposite moment here. Fy multiplied by the distance there, that would be the full 0.6. So Fy is essentially equal to half of that 800, which is just 400 newtons. And because we know the force in the y direction is 400 newtons, we know the kind of direction that that force AE must be pointing at if we write what its position vector is going to be. We know that the force and position vector are going to be parallel to each other. So if we go ahead and write down what that position vector is, position vector AE, we can write it down in terms of the coordinates that we have. In the x direction, we'd be traveling by this distance here, or half of it, to get to that point E. That'll be 0.4. And what about in the y direction? In the y direction, we'd have to travel vertically. We know that the distance between the centroid and point E is 1.7. If we go ahead and subtract off a half so that we're at this upper surface, then we'd have 1.2. So we know that in the y direction, we're going to travel a positive 1.2 meters. Okay, so we're kind of traveling along the x direction. We traveled that 0.4, and we traveled, we're still behind that point E, so we need to travel in the z direction now, half of that 0.6, which is 0.3. Okay, so this would be the position vector AE. And we know that the force AE is exactly the same thing. It's pointing in this same direction at least. Its magnitude is just a little bit different. If we write the force AE, it's some scale factor. Let's call this scale factor A. We're going to be using that scale factor on our current position vector to get what the force is. The force and the position vector are parallel to each other. They just have different scalings, right? We could turn this into a unit vector, or we could make this y component of the force, which is something that we know, equal to 400. The only way that we can make that y component of the force equal to 400 is if we multiply this by 400 over 1.2. So we can use that as our scale factor A, 400 over 1.2. So now all we're going to do is find the tension in the cable, which is just the magnitude of that force AE. If we go ahead and find the magnitude using the we're going to go ahead and find the magnitude of that using the Pythagorean theorem here. It would be 0.4 squared plus 1.2 squared plus 0.3 squared. All of these terms would have a 400 over 1.2. So we can kind of just take that out, take this entire thing out, 400 divided by 1.2. And inside of this, we can see there's a 0.4 and a 0.3 squared. That's like a 3, 4, 5 right triangle there. So that'll be a 0.5. And then 0.5 and 1.2, it's kind of like a 5, 12, 13 right triangle. You can go ahead and do the arithmetic here, or you can use the idea of Pythagorean triples to get that it's going to be the square root of 1.3 here. So 400 multiplied by square root of 1.3 squared is just 1.3 divided by 1.2. So it's going to be a little bit more than 400. 400 times 1.3 over 1.2 gives me 433 newtons. And that looks like choice B here, which is the correct answer. So to review what we did here, we're really looking for the tension in that cable AE. And in order to find the tension in that cable AE, we recognize that we can cleverly take a moment about this line BC that will eliminate these forces that we don't care about, and we'll bring into the problem the thing that we do care about, which is just that Fy component. That Fy component of the force AE could be used along with position vector information to be able to find the force vector, that force AE, which we could find the magnitude of and realize that the magnitude of the tensile force, FAE, is equal to 433 newtons. Okay, so in this problem here, we have a truss here and we're asked which of the members in the truss above is a zero force member. Okay, that looks a little bit better. All right, so we have a truss here, and a truss is just made up of two force members. And the idea of a two force member is super important when you're analyzing, right, frames or trusses. And basically, you have an arbitrary member here with no forces along its span, and you'll have pinned. It'll be pinned at both ends. So if you can kind of picture the pins at both ends, I drew those reaction forces in. And if we apply equilibrium here, we know that the sum of the forces, if we sum the moments at one of these ends here, like this one, we know that the only way that you could produce a zero valued moment is if the force at this end is um, pointing towards or away from the joint, right? So it's kind of, if we draw it in green here, we know that that reaction force here must be kind of along this line such that it intersects that moment point and produces zero moment, right? The sum of the moments must be equal to zero. So that force on that side must be pointing towards my moment point here. And what about the sum of the forces? The sum of the forces tells me that if this force is pointing along this line here, like this, and we assume it to be outward, that means that the force at this joint must be equal and opposite here. So you can kind of picture that if you have a two force member, which means that it's pin connected at both ends with no forces in the center of the body, we'll have to have these forces pointing directly away from each other or directly towards each other. And it's kind of has to be in the direction along these two pin supports here, right? So that's the idea of a two force member. And understanding understanding two force members is super important to analyzing trusses and using things like the method of joints or the method of sections and finding zero force members. It's all about being able to draw that free body in your head or on paper. So I'm looking at the reactions at these supports here, and I see that this one is a pin support, so I'd expect two reactions here, and this one here is a roller support. Now, if we kind of look at this entire system, which is made up of all two force members, and we're looking for a force which could possibly be zero, I'm looking at this point D here. And if we draw that joint D, sure, there could be left and right reactions at that joint D, one from the roller support and one from the tension or compression, at that joint D. But there could be no vertical reaction, right? If the sum of the forces in the y direction must be equal to zero, and there can only be that tension or compression in that member AD, that means that that member AD must be equal to zero, right? There's no other force to counteract that tension or compression, so we know that the force in member AD, that must be the zero force member. All right, so it's really about analyzing all of the joints, and you can kind of do it in your head when you're looking for these zero force members. So you can look at those different joints, or you can make different cuts, right? Like when you make a cut right here and you free the body, you can see that all of these forces, all of these members are two force members, they're towards or away from the joint, and none of these would produce a moment about point C. That reaction at D that would intersect that point C in order to have a sum of the moments which is equal to zero. And when we expose this reaction force here, which is pointing towards or away from the joint, this force in member AD must be equal to zero to produce a zero valued moment when we sum the moment about this section that we have. So that's kind of two ways to think about the problem. Okay, so in this problem, we have a frame shown. It has 1,000 Newton load applied at point E. So I'm looking right here. We're looking for that force in member BD. So if you can kind of picture this entire frame here, and we consider it a frame because it's not just two force members like a truss, you can see that there's forces applied not just at the pin reactions, but additionally somewhere in the middle of those members, right? So like at CDE, this member here, we have the pin reaction from point C, but additionally we have the reaction force from BD. kind of pointing up at that joint. So that automatically disqualifies it as a two-force member. And you can kind of picture that as we pull this end down with that 1,000 Newton, this member BD here would want to be compressed or squished. And we would expect that we would basically expect that BD, which is a two-force member, it's pin connected at both ends, no other forces in the center, it would be experiencing compression. Okay, so we're looking for the force in member BD, and what we're really going to want to think about is the knowns and unknowns and the free body diagram and set of equations that will get us to the solution as fast as possible. If we kind of separate this entire body from its cantilevered support here, then what we'd see is that we'd expose a vertical, a horizontal reaction force, as well as a reaction moment. And none of those are going to help us get any closer to finding the force in member BD. If we isolate this vertical member here, we'd have all of those unknown reactions. We'd have additional reactions at C. And this is a two-force member, so it does bring into the problem what we're looking for, but it's so many unknowns. We have 6 unknowns and only 3 equilibrium equations in 2 dimensions, right? We have sum of forces in the horizontal and vertical direction, as well as some of the moments about the z-axis. So that's 3 equations, and we already have so many unknowns. That's not going to work. If we look at this kind of inclined member here, this is the perfect place to draw a free body diagram, because what we're going to have here, if we just kind of sketch out that inclined member, we have an inclined member here at an angle of 30 degrees. And as we separate that point C from its pin support there, we get a CY, a CX, and that two-force member BD is being compressed, and you can kind of picture that member BD here being squished. And we'd expect that at that joint where it's connected, somewhere would have an equal but opposite reaction here. So this would be force BD, and we got the sign correct. So we should get a positive value, and if we get a negative value, we know something is wrong there. And we have the 1,000 newtons on the right hand side. 1,000. So this is the free body diagram that we need. If we could work out some of these angles, for instance, like the angle from the vertical, which would be the same thing as this angle right here, then we'd have everything that we need to take a moment at point C and find the unknown force, BD. Okay, so how are we going to do this here? What we're going to need to do is find that unknown angle. That's this angle right here. And it's this angle on this triangle. If I highlight it here, a little bit more clear. Now, we know that it's 30 degrees on the inside of that triangle, plus the 90. That means this entire angle here is 120 degrees. Let's separate this off the figure so it's a little more clear. Looking for that red angle there. And we know the side length there is 3. Here, it's 4 here. And we have this unknown side length L and this unknown angle here, theta. How could we find that theta? We can't use the law of sines yet because we don't know enough angles, but we could use the law of cosines to find that side length L, and then we'd be able to apply the law of sines. So let's go ahead and find that angle theta. First, finding that unknown side length L, applying the law of cosines. That says that L squared is equal to A squared plus B squared minus 2AB. Cosine of the angle opposite that side length L, that's 120 degrees. The cosine of 120 degrees is negative 1/2 here. And I'm seeing a 3, 4, and 2. That makes 24. Negative 24 divided by 2 is a positive 12 here with that negative sign. 3, 4, 5 right triangle. So I have a 25 plus a 12 here. That's equal to 37, which is L squared. That must mean L is equal to the square root of 37. If we go ahead and apply the law of sines here, we can say that's the square root of 37 divided by the sine of 120 degrees. That's exactly equal to 4 divided by the sine of theta. And we solve for theta. theta right here is equal to the inverse sine of 4 divided by the square root of 37 divided by the sine of 120. Let's go ahead and plug that entire thing into our calculator here. Square root of 37 divided by the sine of 120. 4 divided by that answer. We're going to go ahead and find the inverse sine of that. Inverse sine of this answer. So I get that angle theta is 34.72 degrees. So that's great. We know the angle theta, and that is this angle right here. Now, what I'm thinking is that we split up that force BD into a force that's parallel, and a first force perpendicular to the member, such that the parallel force will intersect this point C that we're taking a moment about, and the perpendicular force will be the only force producing a moment. So let's go ahead and work out one more of these angles here. We know that that's theta, and we have the perpendicular to that member CDE, and we have the theta here. Now we just need the force, I guess one of these angles here. We know that this is 30 degrees, such that this angle right here should be 90 minus 30 minus that angle theta. So knowing that, we pretty much have everything that we need to be able to split that force into components which is parallel and perpendicular to that surface. Okay, so we're going to go ahead and finish up this problem now. You can see that I labeled that angle right here, the angle of interest that we need to be able to break down FBD into a component which is parallel to the member and perpendicular to the member. I labeled that as angle phi. 60 minus theta, where theta is given down here as 34 degrees. 60 minus theta is around 25.3 degrees. So let me just label that. Phi is 25.3 degrees. So let's go ahead and sum the moment about point C. And you could see that the only unknown there is the magnitude of that force inside of our member of interest, BD. And we'd be able to solve for that after applying this moment equation. We know that the parallel component, that's this component, the cosine component, isn't going to be producing any moment, but the sine component will. FBD, sine of phi. That's the force that's going to be producing the moment and the distance. You can see it right here. The distance between where BD is applied and the point C is 4 meters. So that'll be kind of this distance right here. And it's important when you're taking a moment, you're looking at the perpendicular distance, pretty much the closest distance to that force's line of action. You could see for that 1,000 Newton, for instance, it's going to be this distance right here. That's 8 cosine of 30 degrees, or 8 root 3 over 2. Okay, so that FBD perpendicular component must be producing a moment that balances the 1,000 Newton force placed at a distance of, perpendicular distance of 8 root 3 over 2. You can see the 4 times 2 is 8, which is going to cancel with this. So the answer is 1,000 radical 3 divided by the sine of 25.3 degrees. I get that FBD is approximately equal to 4055 newtons. 4055 newtons, it's pretty close to 4056. So the answer is short C there. In this problem here, we're looking for the polar moment of inertia about the centroidal axis of this symmetric cross section, which is shown above. You can see that I drew X and Y axes up here. And what we're looking for is this term J. Let's go into the FE reference manual. This will be a good practice to kind of be able to navigate that manual. And I already have the relevant section pulled up here, but I'm in the static section because this is a statics problem. And we're looking for things related to moment of inertia, specifically the polar moment of inertia right here. You could see that by definition, the polar moment of inertia is the integral of x squared plus y squared dA. And that kind of brings in some of these terms over here. So J is actually the sum of Iy and Ix. So what I'm thinking is in this problem, instead of using the J formula, what we could do is sum the Iy and Ix, uh, which is a pretty typical problem, right? Finding the moment of inertia about the y-axis, y centroidal axis, and x centroidal axis. We could pretty easily do that, and we just sum them together to get J. Now let's talk a little bit about what the polar moment of inertia is. It represents area distribution, specifically this kind of radial distance, right, distribution here. Same thing for Iy and Ix. Another thing, moment of inertia is known as the second moment of area, right? So you could see these square terms up here. That's as if we took two moments, right? And some people have questions about why Iy involves x terms and why Ix involves y terms. But think about the moment that a small differential area would produce. We go down to this schematic here. You could see a differential area here. You could see the x and y axis. If you took a moment about the x axis, you'd be using y distances to take that moment, right? So the moment about the x axis, or Ix, if we took a second moment, we'd involve y terms, right? That's why Ix is the integral of y squared dA. Iy, or the second moment of area about the y-axis, would involve x distances here. So that's why Iy is the integral of x squared dA. And then J is just the sum of the two. Okay, so the strategy here is going to be to just go down to the actual tables here, moment of inertia tables, and we're going to find the moment of inertia of a rectangle. And we're going to avoid the parallel axis theorem because we're going to take these shapes in a specific way to avoid the parallel axis theorem. But the parallel axis theorem just allows you to um, use the moment of inertia about the centroidal axis of a body and translate it uh, to a specific set of axes here. So if you found it about the centroidal axis, let's say we found the moment of inertia of this right side here about the centroidal axis. That's not the moment of inertia that we're looking for. That's about its own centroid. We'd want to take this and translate it over here, right? A specific distance, and then we'd be able to find the moment of inertia about the y-axis for that shape. We're going to avoid all of that though. We're going to pick our shapes cleverly to be able to avoid them. I'd recommend that you memorize the moment of inertia of a rectangle is super common about the centroidal axis, and the parallel axis theorem, I recommend you memorize that too. The moment of inertia of uh, a rectangle about the x centroidal axis is just base times height cubed over 12. And the moment of inertia about the y-axis, if you kind of rotate by 90 degrees, the base now becomes your height, right? So it's like height times base cubed over 12. Okay, now that we understand all of that information, a good thing here is that J, you could see, is just the sum of Ix and Iy, right? So that all is consistent here. Let's go ahead and apply some of this knowledge that we have. So in general, J is going to be equal to the sum of Ix plus Iy. So what we're going to do is find Ix and Iy, and then just sum them together to find J, and we'd be able to answer this question. Okay, so let's denote the small side b. So b is equal to 4 centimeters, and b is equal to 4 centimeters, h is equal to 8 centimeters. So what we really have is like this. This side is b, this side is h, this side is h, this is b here, the thickness, b, h. Okay, so firstly, let's start off with the moment of inertia about the x-axis. And I picked the moment of inertia about the x-axis to start off with because that would never involve the parallel axis term. You could see that if we mark off the centroid of each of these three bodies here, they all intersect the x-axis. Because all of these bodies have no distance to the centroidal x-axis, we can just sum all of their moment of inertias. So the moment of inertia about the x-axis, which is shared by all of these bodies, is equal to, for that central shape, it's going to be hb cubed over 12. That's this center shape right here. Base times height cubed over 12 plus, and then these other two shapes will just be doubled because they have the same moment of inertia. And then that's just be h cubed over 12. So Ix is just going to be, what about for Iy? Now, when we look at Iy, if we draw in the kind of y-axis to try to visualize, you could see that there's three distinct y-axes that would pierce through the centroid of these bodies here. And there's a specific distance between these bodies. So instead of, this would be the distance here that we would need to translate using the parallel axis term. Instead of doing that, what we're going to do is take the shape. We're going to use addition and subtraction to be able to align all the shapes that we choose with the y-axis of this body, the centroidal y-axis of this body. I'm going to take the first shape as the entire rectangle shown here, and then I'm going to subtract off these small windows here. And you could see that if we took a rectangle and subtracted off those two windows, we'd get this I-beam that's kind of on its side. And the benefit of this is that these two windows, you can picture they're aligned with the y-axis here. So that means there is no distance between these shapes and their centroid and the overall centroid of the body here. Okay, so let's go ahead and do that, right? Iy for the overall rectangle, we have alignment with the overall y-axis. Now recall that Iy is this base, which is a height h, multiplied by this height, which is going to be 2b plus h cubed over 12. So we have that, and we're going to subtract off those two windows. So the Iy for that shape is going to be 2 times the base here is going to be h over 2 minus b over 2. H over 2 minus b over 2 multiplied by this height term, which is just that height h cubed over 12. If we simplify this a little bit, Iy is equal to, so j is going to be the sum of Ix and Iy. We're going to have a 1/12 on the outside here. We have hb cubed plus 2bh cubed. I just wrote down the Ix term here. And then we're going to add the Iy term, which is h multiplied by 2b plus h cubed. So let's plug in h equal to 8 and b equal to 4 into this equation to get a j value equal to 2944, and all of these were in centimeters. I know j is the integral of r squared dA. R squared is centimeter squared. A is centimeter squared again, so I know the result has to be in centimeters to the fourth. If j is 2944, that means it's this answer right here, 2944. So that should be the correct answer there. And there's a part B to this problem. It says, if one end of the cross-section above is removed, the horizontal location of the centroid from the removed end is most nearly. Okay, so what we end up with if we kind of removed, I'm going to draw this in green here so it's more clear. If we removed one of these sections here, we'd end up with a T section, kind of flipped on its side, and we're looking for the horizontal location of the centroid. So that's pretty much this kind of this shape down here. Let me move over a little bit. We have a kind of T shape. And why I included this problem is to point out something super important about the idea of a centroid. Now, centroid is just the first moment of area. And how I picture taking the centroid is what we have here is side length of 8, 4 here, and then this is 4, and this is 8. So what's interesting about this is that the area above and below this kind of point where the T comes together is equal, right? But remember that when you're looking for the centroid, what's special about the centroid is that to the left and right of the centroidal axis, the moment of area must balance, not the area, right? So this is more of a conceptual question. Some people might place the centroid right here, right? Because the areas are equal. We're not looking for equal areas. We're looking for equal moment of areas. So while their areas are equal, the distance, right? The product of the area and distance is not, right? And that's what we're looking for at the centroid of the body here. Okay, so fundamentally, the centroid is equal to, if you kind of, I usually kind of picture an axis here. Picture it hanging off the side of a table, and what I'm doing when I'm taking the centroid here is I'm taking a moment of this area, place the centroid right there, and a moment of this area, and saying that that must be equal to the total area placed at a special distance away. Area 1, x bar 1, that's this moment right here, plus area 2, x bar 2. The moment produced by this system, that's essentially the sum of the moments of the system that we view as two separate rectangles, must be equal to the total area, that's just area 1 plus area 2, placed at a special distance away, that's what we call as x bar. So the moment produced by this kind of separated system, the two rectangles, has to be equal to the combined area, the moment produced by the combined area. So if we wanted to find what x bar is, we could do that, right? We could just, that first area is 8 by 4. That's 32. Multiplied by the x bar, which is half of 8. That will be 4. So I'm looking at this distance right here. That's half of 8. Now, what about for the second area? Same area. So that's the same 32. Multiplied by that distance. That distance is just going to be 8 plus half of this 4. 8 plus half of 4 is 10. And we divide by the overall area, that's just double 32 or 64. So you can see that I can get rid of all of these 32s here. Put a divide by 2 here. I have 14 over 2, so the solution there is 7. X bar is equal to 7 centimeters. So that's the solution right here. 7 centimeters, and this one was 29.44 centimeters to the fourth. Okay, why is that 7 interesting? Because you could see that if you placed an axis right here at that 7 centimeter mark, 7 centimeters from this y-axis located here, what you could see is that this area right here would be 7 by 4. And this area right here would be 8 by 4 plus this little unit area, plus this little extra area right here, which would be, I guess, 1 by 4 here. In this configuration here, the moment produced by this 7 by 4 area and the moment produced by in the other direction by this small area and this large area, they're exactly equal. And because they're equal, if you place like let's say you place this shape on a wire at that point, it would balance, right? Left and right, and you would expect it to stay in perfect balance there. In summary here, if we place an axis at the centroid, intersecting that centroid point, the moments of areas left and right of that axis will be in perfect balance, and we'd expect that object to stay in equilibrium. Now, this idea of moments of areas confuses some people, right? Note that if we placed this physical object at the edge of a table, let's say we actually had an object with thickness with a certain density, we can compute its weight, right? The weights and however we split it up. However, the easiest way for us to split it up, like an easy way to split up the shape for us, was into two rectangles. We can find the weights of each of those rectangles, and those weights placed at a distance would produce a moment. In general, weight is just mass times gravity, and the mass can be computed by density times volume, or the volume could also be computed as the area times the thickness times gravity. This entire term represents a weight, and we multiply that weight by a centroidal distance. So let's say we replaced each of the area terms by density, thickness, area, gravity. Each of these terms, the density, the thickness, and gravity are all common. So we end up crossing them out left and right side, and we end up producing moments of areas. But actually, we're just actually taking a moments of each of these weights, right? That's what's actually producing the moment. It's just common density, thickness, and gravity make it look like moments of areas. Now, when I'm thinking about the centroid formulation, I'm thinking about also the idea of statically equivalent systems, right? The idea that we wrote down in this relation right here is that the moment produced by these two rectangles is the same as the total system placed at the centroidal distance. That's the same thing as the idea of statically equivalent systems because the sum of forces has to be the same. That's why area 1 and area 2, and you can see the combined area here, and the sum of the moments has to be the same for the two systems, and that's what I'm writing down right here. Connecting these different ideas helps you to retain more information. When I'm thinking about centroids, I'm thinking about statically equivalent systems. I'm thinking about distributed loads. And when you practice a problem like this, you're able to practice those other problems as well in unison. And repeatedly seeing these ideas will help you retain the information better. In this problem here, we have a 25-pound block. It's placed on a 30-degree inclined plane, which is attached via cable and pulley to a 20-pound mass. Remember the idea of the English system, right? They put gravity inside the definition, right? 1 pound force is equal to the amount of force is necessary to accelerate 1 pound mass at a rate of 32.2 feet per second squared. Because they put gravity inside of the definition, we know that 25-pound mass is the same thing as 25-pound force. So actually, the weight here is 25-pound force. And while we say 20-pound mass here, it doesn't matter. We put 20-pound force. It's equivalent, right? The magnitudes are equivalent. If we take 20-pound mass, multiply it by gravity, we get 20-pound force. It says if the friction coefficient between the inclined surface and the block is 0.3, so we know that mu, friction coefficient, the static friction coefficient is 0.3, the block will, and we're looking to see, will it slide up, slide down, will it stay still, or is there not enough information for us to make that determination? Now, the first thing I want to discuss is the misconception about friction, right? If we placed a box on a table, we know that it will have a mu value, it will have a weight value, it'll have a normal force, which is opposing that weight. So we know that the friction force is equal to mu times the normal force. But this is not always what the friction force is equal to. If the box is sitting on the table and the friction force was equal to mu times n, we'd expect this box to go flying left or right? But that's not what it's doing. This friction force, which is the product of mu times n, is the maximum possible friction force. Friction is self-adjusting. So if I apply 1 pound here, that means that the friction force will oppose that motion. It will oppose that force with a magnitude of 1 pound. If I apply 2 pounds, it'll oppose 2 pounds. If the maximum possible friction force, let's say, is 10 pounds, and I apply 10 pounds, the friction force will adjust to 10 pounds. But if I apply 10.1 pounds, I've broke through the maximum possible friction force, I'm going to have motion because there's a net force in a specific direction. The friction force is self-adjusting up to a certain point, and that certain point is the product of mu times n. So in order to find what the friction force is in this system, we're going to go ahead and draw a free body diagram. We already have the weights on this orange block here. We can go ahead and draw in a normal force. And you know that 20-pound force is going to have a tension here. That's 20-pound force, pound mass, doesn't matter. And we have a 30-degree angle here. Note that the 30 degrees is right here. That's this same angle right here. Let's denote that as an angle theta. Now, the last thing that we're missing is which direction should we place the friction force? And usually to decide on the direction that I'm going to place the friction force, if this is theta, this is 90 minus theta. That means this angle right here is theta as well. Usually to decide which direction I'm going to place the friction force, I look at, let's say the system had 0 friction inside. Which direction would this block want to slide? We have 20 pounds in the x direction. Let's call this the x direction here. And let's call this the y direction here. We have 20 pounds in that direction, and we have 25 sine of theta. The sine of 30 degrees is equal to 1/2. So 25 divided by 2, that's 12.5. If I look at the difference between this 20 pounds and the 7.5, which is kind of this, let me draw this in a different color so it's more clear. This 25 pounds could be split up into this, which is 25 sine. 25 sine of theta, that's going to be equal to 12.5, or 25 divided by 2. 12.5 and this 20 pounds, I could see that the net motion would want to be upwards if there was no friction in the system. Friction always opposes the motion, so that means I should draw the friction force downward, down the plane, right? It'll oppose that motion. So this is my force due to friction, and I don't know what that's going to be, right? I know it's going to be self-adjusting up to a certain point. So what I'm going to do is I'm going to solve for what that friction force is going to be, and then I'm going to check it against the maximum possible friction force. And if it's under that friction force, then I know it's going to stay still. If it's over, then I know it's going to be sliding up. So I'm going to remove some of this here so I have some space to write. And all I'm going to do here is sum the forces in the x direction. And I'll be able to solve for what exactly the friction force is. There's only one unknown there. It's the friction force. And I'm going to compare that to the product of mu times the normal force. Okay, so firstly, let's go ahead and sum the forces in the x direction. Let's assume that it's in equilibrium. So if it is in equilibrium, that means I'll have 20 pounds upward. I'll subtract off the 25 sine of theta component, and sine of 30 degrees, we know that's equal to 1/2. And lastly, I have a friction force, which is going to be opposing that motion. That must be equal to 0. If I solve for the friction force, what I get is that the friction force is the difference between 20 minus, remember the sine of 30 is 1/2, so I'll have 12.5 here. The friction force is 7.5 pounds. Now to check to see if it's feasible for the friction force to be equal to 7.5 pounds, what I'm going to need to do is compare it to the maximum possible friction that we can get. The maximum possible friction that we can get is equal to the product of mu times n. We know mu is 0.3, and if we go ahead and sum the forces in the y direction, you could see that the normal force is just going to be equal to that component of the weight, which is normal to the plane in the y direction. Right? That's just going to be 25 cosine. 25 cosine of theta, cosine of 30 degrees. We know what the cosine of 30 degrees is. That's going to be the square root of 3 over 2. So 25 over 2, that's 12.5 multiplied by the square root of 3. So 25 root 3 times 0.3. The maximum possible friction that we can have in this configuration is 6.49495 pounds. If I compare my maximum possible friction to the friction force required for equilibrium, I see that my friction force that I'm calculating for this thing to be equilibrium is even greater than the maximum possible friction. So we've had to have broken through the maximum friction barrier. And that means motion is going to ensue in that direction that we saw the net force would be. That means the block is going to be sliding upward. So these friction problems are tricky, but just understanding the idea, think of that block placed on a table and the idea of the maximum friction force. Remember that the friction force is not the product of mu times n. That is the maximum possible friction force, and that friction is self-adjusting. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top three subjects, what are my bottom three subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $9.99. Let's get back into the video. If you made it this far in the video, thank you so much for watching. If you like content like this, consider leaving a like and subscribing. And you can leave a comment down below. Let me know what review you want to see next. I'm thinking of a dynamics or thermodynamics review, but let me know what you think in the comments down below. Thank you for watching the video. I'll see you in the next one. Goodbye.